Welcome. Today we're diving into the world of register transfer language, or RTL. RTL is a fundamental concept in computer architecture and digital design. It's a symbolic language used to describe the operations, data transfers, and transformations that occur between registers within a digital system. By understanding RTL, you'll gain insight into how computers execute instructions at the hardware level. Let's start by exploring what RTL is and why it's so important in designing and analyzing digital circuits. Register Transfer Language, or RTL, is a set of notations used to specify the sequence of operations in a digital system. It describes how data moves between registers and how operations are performed on that data. RTL is not a programming language, but rather a way to represent the flow of data and control signals at the hardware level. This makes it an essential tool for hardware designers and engineers, as it bridges the gap between high-level algorithms and actual circuit implementation. RTL plays a crucial role in digital system design because it allows engineers to precisely describe how data is processed and transferred within a system. By using RTL, designers can create clear and unambiguous specifications for hardware behavior. This clarity is vital for verifying that a design will function as intended before it's built. RTL also serves as the foundation for hardware description languages like VHDL and Verilog, which are used to create real-world digital circuits. At its core, RTL uses simple notations to represent data transfers and operations. For example, the statement R1 left arrow R2 means that the contents of register R2 are transferred to register R1. Similarly, R3 left arrow R1 plus R2 indicates that the sum of R1 and R2 is stored in R3. These notations help designers visualize and plan the sequence of operations that a digital system will perform. Registers are small, fast storage elements within a CPU or digital system. In RTL, registers are the primary locations where data is stored and manipulated. Each register is typically identified by a unique name, such as R1, R2, or ACC accumulator. Understanding how registers interact is key to mastering RTL, as most operations involve moving or transforming data between these storage elements. Let's look at a simple data transfer example in RTL. Suppose we want to copy the value from register R2 to register R1. In RTL, we write this as R1 left arrow R2. This operation is fundamental in digital systems as it allows data to be moved where it's needed for further processing. Such transfers are the building blocks of more complex operations. RTL can also describe arithmetic operations. For example, if we want to add the contents of R1 and R2 and store the result in R3, we write R3 left arrow R1 plus R2. This notation clearly shows the source registers, the operation, and the destination register. Arithmetic operations like addition, subtraction, and logical operations are all easily represented in RTL. RTL can express conditional operations, which are essential for decision-making in digital systems. For example, an RTL statement might specify that data should be transferred only if a certain condition is met, such as if z equals 1, then R1 left arrow R2. This allows designers to model control flow and branching, which are key aspects of computer programs and hardware. Control signals are a vital part of RTL. They determine when and how data transfers and operations occur. For instance, a control signal might enable a register to accept new data or trigger an arithmetic operation. By specifying control signals in RTL, designers can coordinate complex sequences of actions within a digital system. RTL is heavily used in CPU design to specify how instructions are executed. Each instruction, such as ADD or load, can be broken down into a series of RTL statements that describe the movement and processing of data. This level of detail helps engineers design CPUs that are both efficient and reliable. Microoperations are the individual steps that make up a CPU instruction. RTL is used to describe these microoperations, such as fetching data from memory, performing arithmetic, or storing results. By breaking instructions into microoperations, designers can optimize hardware for speed and efficiency. Let's see how an ADD instruction is represented in RTL. Suppose we want to add the contents of registers R1 and R2 and store the result in R3. The RTL statement would be R3 left arrow R1 plus R2. This simple notation captures the essence of the operation, making it easy to understand and implement in hardware. A load instruction moves data from memory into a register. In RTL, this might be written as R1 left arrow M100, meaning the contents of memory location 100 are loaded into register R1. This notation helps designers specify exactly how and where data is moved in a system. The store instruction is the opposite of load. It moves data from a register to memory. In RTL, this is written as M100, left arrow R1, meaning the contents of register R1 are stored in memory location 100. This operation is essential for saving results and managing data in digital systems. The control unit of a CPU uses RTL descriptions to generate the necessary signals for each operation. By interpreting RTL statements, the control unit knows when to activate registers, perform arithmetic, or access memory. This coordination is what enables the CPU to execute instructions correctly and efficiently. In hardware design, RTL serves as the blueprint for building digital circuits. Designers use RTL to specify how components like registers, ALUs, and memory interact. This high-level description is then translated into hardware description languages and eventually into physical circuits. RTL is closely related to hardware description languages like VHDL and Verilog. These languages allow designers to write RTL-level descriptions that can be simulated and synthesized into real hardware. Understanding RTL is essential for anyone working with these languages, as it forms the basis of digital design. Before building hardware, designers use RTL simulation to verify that their designs work as intended. Simulation tools execute RTL descriptions, allowing engineers to test and debug their circuits in a virtual environment. This step is crucial for catching errors early and ensuring reliable hardware. Let's visualize a simple RTL operation. Imagine two registers, R1 and R2, and an adder. The operation R3 left arrow R1 plus R2 is performed by connecting R1 and R2 to the inputs of the adder, and the output goes to R3. This schematic shows how RTL statements map directly to hardware components and connections. Optimizing RTL descriptions can lead to faster and more efficient hardware. By minimizing the number of operations or reusing hardware components, designers can improve performance and reduce costs. RTL optimization is a key step in creating high-quality digital systems. In summary, register transfer language is a powerful tool for describing and designing digital systems. It provides a clear and precise way to specify data movement and operations at the hardware level. Mastering RTL is essential for anyone interested in computer architecture, digital design, or hardware engineering. Thanks for joining this exploration of RTL.